Welcome back to the deep dive. Go ahead and grab your warmest blanket, maybe a cup of tea, just settle in.
Yeah, we've got the mood lights down low for this one.
We really do. We're deep into that late night stretch where the world outside has finally gone quiet.
And the inside of your mind feels like it's ready to absorb some truly strange ideas.
Exactly. It's the perfect time for what we're doing tonight. We've spent weeks, just diving deep into our reading.
We've been pulling articles, really complex papers, decades of scientific notes, and our mission really is to explore the 100 biggest, most fundamental questions that science it just can't answer.
Yeah, this isn't about, minor technical stuff we'll figure out next year.
No, not at
This is about the foundational structure of reality itself. The things that, right now, force world-class physicists and biologists to just kind of look at each other and admit.
We have absolutely no idea what's going on.
Exactly. It's wonderfully humbling, isn't it?
It's the ultimate reality check. I mean, for all the brilliance humanity has shown, mapping the universe, landing rovers on Mars.
Developing vaccines overnight.
Right. We still live inside a universe that is just defined by these profound, quiet mysteries. We're talking about fundamental gaps in our understanding.
And it spans everything, from the entire cosmos to life on Earth to our own minds.
Science at this level isn't some finished authoritative book.
No, it's more like an ongoing, infinitely strange story. And frankly, the mysteries are the best chapters. We're going to be your guides through the ultimate cliffhangers.
So let's just jump right in. We're starting with the absolute biggest concept possible before we narrow it down to the weirdness happening right here on our own planet.
Okay, let's unpack this. You really have to start with the ultimate question, don't you?
You do.
It's the one every 3-year-old asks their exhausted parent. And it's the one our reading highlighted as. It's the foundational mystery of all existence.
Why is there something instead of nothing?
Exactly. Why is there all this instead of just nothing?
It sounds like a philosophical parlor game, but for cosmology, it's a real immovable barrier.
Right. Modern physics can trace the timeline of events back, 13.8 billion years?
Pretty much right to the brink of the Big Bang, yeah?
Yeah.
It tells us how the universe has evolved, how gravity works, how stars ignite.
But it offers absolutely zero explanation for why the Big Bang happened in the first place.
Or just why the universe exists at all.
It's like having the full history of a massive novel, every plot twist, every character arc.
But the cover is blank.
Yeah, the cover's blank, and you can't figure out who wrote it or why they even have bothered.
Precisely. And the traditional answer, that there was truly nothing before, well, that's been fundamentally challenged by quantum mechanics.
Oh, this is where it gets really, really interesting.
Our research dives deep into this, and it's a mind-bending concept. What we call nothing is actually violently unstable.
Right. You imagine the vacuum of space, far away from any stars, as just pure emptiness. Black, silent, nothing.
But at the quantum level, it's a chaotic zoo.
It's boily.
It is. The vacuum just teems with these virtual particles, or these fleeting antagonistic pairs of matter and antimatter that constantly pop into existence.
And then immediately annihilate each other.
Instantly. They flicker in and out of reality so fast, they don't violate the law of conservation of energy. It's like they borrow energy for the absolute briefest of moments.
So the vacuum isn't empty. It's a low-level, chaotic froth of potential existence.
Exactly. And this instability has led a lot of physicists to suggest that maybe, just maybe, absolute non-existence is physically impossible.
Wow.
The lowest energy state of the universe might not be a true empty nothing, but this highly unstable state that is constantly churning out something.
So our entire universe could just be the largest, longest-lasting quantum fluctuation possible.
It's one of the leading ideas.
That feels profoundly unnerving. So existence isn't some miraculous anomaly. It's the inevitable, natural state of reality.
And non-existence is the statistical failure.
Okay, but even if we accept that, that just bumps us into another problem, right? The multiverse theory, which, as a concept, I love it. It's so cool.
It's deeply satisfying.
But logically, for this question, it's a dead end.
It's the ultimate mystery multiplication machine. The multiverse hypothesis suggests our universe is just one of countless bubbles in some kind of cosmic foam.
Each with different physical laws, maybe.
Potentially. But if we accept that, we've just shifted the goalposts. Now we have to ask, why does the cosmic foam, the multiverse generator, exist?
We've just multiplied the original question by infinity.
Making it even harder to solve. It's the ultimate checkmate.
And the most haunting part, which we're reading really highlighted, is that it's fundamentally an untestable mystery.
Okay.
We can't build a telescope to peer into non-existence. We can't fire a particle at the Big Bang's origin point. This question, the why of being, is entirely inaccessible to science, yet every single branch of physics rests on the assumption that existence is possible.
It's the starting block that we can't inspect.
Okay, so if the question of being is a bit too philosophical for you, let's pivot to a physical reality that's staring us right in the face.
One that defines our entire cosmos.
The sheer, simple fact that 95% of the universe is made of stuff we cannot see, touch, or understand.
I mean, when you put it like that.
It's cosmic embarrassment. We think we're so intelligent, but 95% of reality is giving us the silent treatment.
It is genuinely humbling. We call them dark matter and dark energy, and they are essentially placeholders for colossal ignorance.
Let's start with dark matter. That's what, about 27% of the universe?
Roughly, yeah, about 27% of the total mass energy. And this all started when astronomers noticed that galaxies were, well, they were behaving badly.
They were spinning too fast.
Way too fast. Imagine a massive carousel. If you have stars at the very edge moving at the speeds they're observed to be moving,
They should just fly off.
the centrifugal force should just fling them out into space. They should be lost. But they aren't.
It's like there's an invisible, colossal, spherical anchor just wrapped around every galaxy, holding it all together.
Molding together with immense gravity, and since this invisible stuff exerts gravity, so it's massive, but it doesn't interact with light at all.
It doesn't absorb light or reflect it or emit it,
We call it dark matter. It's transparent, it's silent, and it is everywhere.
and we know more about what it isn't than what it is, right?
That's a great way to put it. It's not just unlit dust or dim stars, because those things would still interact with light in some way. This stuff it's fundamentally different from the protons and neutrons that make up you, me, this table, everything.
And our reading detailed this decades-long hunt for the particle responsible. The focus has been on two main candidates, right?
WIMPs and axions, mostly. WIMPs are weakly interacting massive particles.
And that weakly interacting part is key.
It's everything. It's why they're so hard to find. If WIMPs exist, they pass straight through ordinary matter, through us, through the Earth, through solid lead shielding.
With almost no chance of ever hitting anything.
Exactly. So to catch one, you have to build these incredibly elaborate traps.
Deep underground, right? In old mines or ice fields.
Yeah, to shield the detectors from every other possible source of cosmic noise. And you're basically just waiting for a 1 in a billion collision, hoping a WIMP will just happen to bump into a nucleus in your detector and cause a tiny flash of energy.
And after decades of this,
Nothing. Silence. The experiments keep running, they get more and more sensitive, and the results are consistently null.
which is forcing people to think maybe it's not a particle at all.
It's forcing physicists to broaden the search, to consider that maybe dark matter isn't a particle, but, I don't know, a modification of gravity itself at large scales. But that theory has its own huge problems.
So that's the bizarre anchor holding galaxies together. Now for the really wild part, dark energy.
The stuff that pushes.
This accounts for, what, nearly 70% of the universe?
Roughly 68%, yeah. And it's a concept that was invented specifically to explain a shocking anomaly they discovered back in the late 90s.
The great cosmic surprise.
It really was. Astronomers were expecting the expansion of the universe, the thing that started with the Big Bang, to be gradually slowing down.
Because of gravity, right? All the stuff in the universe should be pulling on all the other stuff.
The mutual gravitational pull of all matter. It was a standard classical expectation. You throw a ball up in the air, you expect it to slow down and maybe fall back.
Or at least coast to a stop.
But instead, they found the exact opposite.
The expansion is accelerating.
It's speeding up. The most distant galaxies are rushing away from us faster and faster and faster.
So to explain this anti-gravitational effect, physicists had to invoke a mysterious force.
A force inherent to space-time itself, just pushing space apart. And we call it dark energy.
Which is just a magnificent way of saying
Yeah.
there's this unknown, enormous, repulsive force making up 2/3 of the universe.
And we haven't a clue what it is.
It's not matter. It's some property of the vacuum itself, and it seemed to get stronger as the universe gets bigger.
And its presences. It's far from academic. I mean, dark energy determines the ultimate fate of the entire cosmos.
This is where it gets scary.
If it remains constant, it dictates that the universe will end in a slow, drawn-out heat death.
Everything just gets colder and further apart.
Exactly. Expansion continues, stars burn out. All matter eventually just drifts apart into a cold, empty void. forever.
But that's not the worst case scenario. The one that really keeps you up at night is the big rip.
The big rip. That's what happens if dark energy doesn't stay constant, but instead grows stronger over time.
What happens then?
Well, if its density increases, its repulsive force will eventually overcome the gravity holding galaxies together. They'll fly apart.
Okay.
Then it will overcome the electromagnetic forces holding molecules together.
Oh.
And finally, it will overcome the strong nuclear forces holding atoms themselves together.
Wait. It could literally rip apart the atoms.
Yeah.
The fabric of space-time would be torn apart by this invisible hand that makes up 70% of reality.
That is the catastrophic prediction. The expansion would accelerate so violently that everything, right down to the fundamental particles, would just be shredded.
Wow. So this 70% mystery isn't just about cosmic structure.
It's the ultimate doomsday clock. We are living inside a reality where the vast majority is a completely unknown ingredient dictating whether our future is a slow, cold fade or a sudden, dramatic annihilation.
That is a lot to take in.
It is.
So we're standing on the precipice of non-existence. We're surrounded by unseen matter and energy. And now we have to talk about the one thing we experience every single second: time.
Why does it only flow forward?
It's maybe the most baffling paradox of all, because like you said, we live inside of time's directions so rigidly.
We remember yesterday. We anticipate tomorrow. We age. We can't undo mistakes. It's absolute.
But when physicists write down the fundamental laws of the universe, like Newton's laws or the equations for quantum particles, they're almost all time symmetrical.
Meaning, if you filmed an interaction between two tiny particles, say an electron scattering off a proton,
And then you ran the film backward.
the physics is still totally valid. The equations don't care which way time is flowing. At the smallest scale, time reversal is theoretically fine.
But when you scale up to our world, the macroscopic world, everything is strictly one-directional.
A broken glass never leaps back together.
Milk never spontaneously unstirs itself from your coffee. Disorder always increases.
And that increasing disorder is what gives time its direction. That's the concept of entropy.
Right, the arrow of time is tied to the second law of thermodynamics. The entropy or disorder of a closed system has to always increase.
Time flows forward because the universe is constantly moving from a more ordered state to a more disordered one.
It's like shuffling a deck of cards.
That's a perfect analogy. There's only one way for the deck to be perfectly ordered, ace to king, all suits together. That's low entropy.
But there are trillions upon trillions of ways for it to be disordered. High entropy.
So shuffling, or just the passage of time, always pushes the deck toward disorder.
That makes perfect sense. Our experience of time is just us watching the universe get shuffled from neatness to chaos. But here's the huge paradox, and our reading goes deep on this.
If time flows because disorder increases.
Why did the universe begin in an initial state of such extremely low entropy? So incredibly ordered.
It's the ultimate clean room problem. For time to have this strong, irreversible arrow, the universe must have started out unnaturally tidy, immensely ordered.
If the Big Bang had started out with high entropy, already a big chaotic mess.
There'd be no forward flow of time, or at least not one we could perceive.
So the question of why time moves forward forces us to go back to the Big Bang and ask why the initial conditions were so perfectly, ridiculously organized.
It's as if you threw a deck of cards into the air, and they landed perfectly stacked, ace to king, suits separated.
It should have been a high-entropy mess from the very beginning.
And no one has a satisfactory answer. Some theories suggest the arrow of time emerges from complex interactions, or maybe it's tied to the expansion of the universe itself.
But we're living inside of time's rigid direction every single second of our lives, and the why of its forward march remains one of science's most profound and haunting intellectual dead ends. Okay, that was section 1. And if your brain isn't feeling a little stretched by the sheer magnitude of reality's unanswered questions, I don't know what to tell you.
I mean, we just covered existence itself, the fate of the cosmos, and the fundamental nature of time.
Yeah, no big deal. We've established that the universe is predominantly invisible, dangerously expansionary, and structurally dependent on an improbably clean starting point.
I know, right?
So now we're going to pivot from those huge cosmic questions to things that are almost offensively bizarre, because they challenge our intuition about basic forces in basic life.
This is where it gets really fun.
Oh, yeah. And just to give you a little taste of the pure oddity coming up later, we're going to dissect the fact that a tiny magnet on your refrigerator is powerful enough to overwhelm the gravity of the entire Earth.
That power imbalance is totally necessary for our existence, but we have no idea why it's there.
We're also going to look at the biological secrets hiding in plain sight, like a salamander's ability to regrow a perfect limb from scratch.
And the secret compass that lets monarch butterflies fly thousands of miles to a specific tiny forest they have never, ever visited before, across multiple generations. It's unbelievable.
And finally, we'll ask whether space and time themselves are even fundamental, or if they're just emerging from something deeper, like a pattern of quantum information.
Suggesting our reality is the ultimate illusion, kind of a cosmic hologram.
So what do you think so far? Has the thought of the Big Rip or the entropy paradox ever kept you up at night? Seriously, comment below. We love reading your theories, especially on this kind of mind-bending content.
And while you're thinking about it, if you're enjoying this deep dive, we are a small channel and would absolutely love it if you hit that like button and subscribe to us on YouTube.
It genuinely helps other people find their way to this weird conversation, and it keeps us digging into these wild topics for you.
Okay, so now let's bring things down from the universal scale and talk about what happens when our most established theories of physics completely fail at the edges.
All right, let's talk about the force that makes reality possible. Gravity.
It dictates the orbit of planets, it forms galaxies, it's the master architect of the cosmos.
And yet it is unbelievably weak compared to literally everything else. This is the hierarchy problem.
It is a truly profound puzzle. Physics has four fundamental forces: gravity, electromagnetism, and then the strong and weak nuclear forces.
The nuclear forces hold atoms together, electromagnetism handles light, chemistry, all the stuff we interact with every day.
But gravity is a total wimp in comparison. I mean, it's not even close.
How weak are we talking?
If you compare the strength of the electromagnetic attraction between an electron and a proton in a hydrogen atom to the gravitational attraction between them, the electromagnetic force is stronger by a factor of 10 to the power of 40.
That's a 1 with 40 zeros after it. My brain can't even process that number.
To put it into a perspective, you can use your magnet analogy. Take a cheap little refrigerator magnet.
Okay.
That small piece of metal, driven by electromagnetism, is generating enough force to easily overcome the gravitational pull of the entire planet Earth.
A sphere of rock, 4,000 miles in radius, trillions of tons of mass.
Just to hold a postcard to the fridge.
It's absurd. Why is there this staggering, impossible difference in power? Why is the force that commands the cosmos so weak it can be defeated by a piece of magnetized plastic?
This is the absolute crux of the hierarchy problem. It's a massive fine-tuning issue.
Because if it wasn't this exact level of weak, we wouldn't be here.
Not even close. If gravity were even slightly stronger, stars would burn out and collapse way too quickly. The universe wouldn't have lasted long enough for complex life to form.
And if it were weaker,
matter would never have coalesced into galaxies or planets in the first place. Its strange, specific weakness is essential for our existence, but we have no theoretical model to explain the reason for that weakness.
our reading suggests a few truly wild theories trying to solve this.
Yeah.
The favorite seems to involve extraspatial dimensions, which, I mean, that sounds like something straight out of science fiction.
It does, but it's mathematically sound. The theory suggests that maybe gravity isn't actually weak,
It just looks weak to us.
because its power is being diluted. Imagine our observable universe, 3 spatial dimensions, is like a sheet of paper.
Okay.
All the other forces, electromagnetism, the nuclear forces, they're all stuck to that sheet of paper. But gravity, the theory posits, is capable of leaking or spreading into hidden, curled-up dimensions that we can't perceive.
So it's paying rent in too many dimensions, and we only get the residual strength here on our little sheet of paper. That's
Yes.
why it feels so weak.
Exactly. The total gravitational force might be just as strong as the strong nuclear force, but 99.99999 whatever percent of it is operating beyond our spatial perception.
That would solve the problem instantly.
It would. But of course, we have yet to find any direct evidence for these extra dimensions. It's an amazing example of how sometimes, to solve a puzzle in physics, you have to propose a truly fundamental rewrite of reality itself.
So if we follow the trail of gravity to its absolute logical extreme, we end up at the black hole.
Which is maybe the most fascinating failure of human understanding.
The point at its center, the singularity, that's literally where our math throws up its hands and quits.
It is. The singularity is the point where Einstein's theory of general relativity predicts that all the mass of a collapsed star has been crushed into a point of zero volume and infinite density.
And infinity is usually a bad sign in math.
Infinity is the mathematical signal that your physical model has broken down. It's a giant red flag that says you need a better theory.
Because we know general relativity describes gravity beautifully on large scales.
And quantum mechanics describes particles beautifully on small scales.
But inside a singularity, you have immense gravity acting on an infinitesimally small volume. You're forced to use both theories at the same time.
And they just don't play well together. They're antagonistic.
So until we have a theory of everything, a unified theory that harmonizes gravity and quantum mechanics,
The true physical nature of the singularity remains completely sealed away behind the event horizon. It's a total mystery. It's the ultimate signpost saying, beyond this line, you need a different rule book.
and if the singularity wasn't a big enough headache, you have the information paradox.
Which challenges the deepest foundations of quantum physics. This is a huge, huge deal.
Okay, break it down for us.
Quantum mechanics rests on a fundamental principle. Information is never, ever destroyed. If I take a piece of paper, shred it, and then burn it, the information, the location and state of every single atom is still preserved in the smoke and ashes. It's still there. It's just scrambled.
Right. But when matter falls into a black hole, it seems to just vanish forever.
It only contributes to the black hole's mass, charge, and spin. All the delicate, unique information about what that matter was, whether it was a puppy or a textbook, is apparently gone, wiped from the universe.
If that information is truly destroyed,
The entire framework of quantum mechanics collapses. It fundamentally violates the preservation of information. This is why Stephen Hawking proposed a theoretical escape route for it.
Hawking radiation, the idea that black holes aren't truly black.
Correct. He predicted they slowly evaporate over cosmic time. He theorized that quantum fluctuations near the event horizon would cause the black hole to emit this faint thermal radiation.
And that radiation would carry the information back out.
Theoretically, it would carry the scrambled information away as the black hole shrinks. It's the universe's cosmic recycling program.
But there's a problem. Right.
Two problems, really. One, we have never directly observed Hawking radiation. It's far too faint, completely overwhelmed by all the violent, hot material surrounding any real, active black holes in space.
And the second problem.
Even if it exists, physicists cannot agree on how that radiation carries the information without violating other laws of physics, like causality. You can't have information escaping faster than light, for example.
So you have this physical object, the black hole, that forces a philosophical and physical paradox. And the only potential solution is a theoretical effect we can't detect, and which, even in theory, causes all sorts of other headaches.
It strongly suggests that our current understanding of reality, of causality and information, is fundamentally flawed at the extremes of existence.
That's profoundly tantalizing. And since we're talking about fundamental flaws in our understanding, let's leave the cosmos for a bit and dive into the bizarre flaws and triumphs of life right here on Earth. I love this transition. We're going from a black hole that destroys information to a tiny animal that can spontaneously rebuild it.
Regeneration.
I am talking about regeneration. The fact that a salamander or a newt can perfectly regrow an entire limb, bone, nerves, everything, and we can't, is genuinely infuriating.
It is. I mean, think about what that process actually involves. You're repairing muscle, rebuilding bone structure, recreating the entire complex network of nerves, connecting the circulatory system.
All perfectly aligned.
Perfectly. And we humans, we share much of the same fundamental DNA toolkit as these creatures. But our repair mechanism defaults to scarring.
Just quick, fibrous, permanent damage control.
Exactly. The running theory is that scarring is just faster, and in the wild, fast repair means survival. You patch the hole before you bleed out or get an infection.
But the biological secret of the salamander is so much more complex. When its limb is severed, the cells at the wound site, instead of forming scar tissue, they de-differentiate.
De-differentiate. What does that mean?
They perform a genuine biological reset. They transform into this flexible mass of stem cell-like tissue called a blastema, so they forget what they were.
Yes. They lose their specific identity. A skin cell stops being a skin cell. A muscle cell stops being a muscle cell. They become pluripotent again, capable of building anything.
And then this blastema grows outward.
And it reads the information from the remaining limb stump to perfectly recreate the missing structure, right down to the specific bone shape and the nerve connections.
That is effectively magic. It means the information for building a whole limb is permanently stored in the adult body, ready to be activated.
And humans, it seems, have just misplaced the key to that activation.
Our reading suggests that if we could unlock even a fraction of this, we could revolutionize medicine. Healing damaged spinal cords, heart tissue after a heart attack, severe burns.
It's one of biology's greatest prizes. And tied closely to this idea of perfect repair is the mystery of extreme longevity.
Whereas certain creatures seem to just laugh at the rules of aging.
Most animals follow a general size to lifespan correlation, right? Big animals live long, small animals live short,
But then you have these beautiful outliers, the Greenland shark.
which can live for over 400 years, just slowly drifting through the Arctic deep.
Or the bowhead whale, routinely living for over 200 years. They defy the expected laws of biological decline.
And the bowhead whale specifically presents a massive paradox. It's known as Peto's paradox.
I remember this one. The more cells an animal has, and the longer it lives, the greater the statistical chance that one of those cells will develop a cancer-causing mutation.
Correct. A bowhead whale has billions upon billions more cells than a mouse, and it lives 10 or 20 times longer. This gives mutations ample time to accumulate.
By all statistical measures, bowhead whales should be riddled with cancer.
But they rarely, if ever, get it.
So they have an unbelievably efficient cancer suppression mechanism that we haven't fully identified or copied yet.
Exactly. Our research points to unique, highly efficient DNA repair mechanisms and specific tumor suppressor genes that have evolved to manage their huge cell count and longevity.
The naked mole rat is another one, right?
Another great example. They live 10 times longer than a similarly sized rodent, and they have these specialized proteins that prevent tumors from forming.
It's proof that aging and death aren't these inevitable biological laws. They're solvable engineering problems.
Nature has already cracked the code for efficient DNA repair and disease resistance in these lucky species. We just need to find the recipe.
And the mystery is that we haven't isolated the exact mechanism well enough to replicate it in human cells.
Yet.
Okay, let's talk about the final and most intimate mystery. We've explored the edges of the universe, but the most complicated piece of known matter is the 3-pound organ sitting inside your skull.
Consciousness.
Consciousness. It's the one thing we all take for granted.
It's the feeling of being you, of experiencing sensation, of thinking about these mysteries we're discussing right now. It is the ultimate enigma.
Because while we know it arises from the brain, we don't know how or why.
We have incredible neuroimaging technology. We can map the physical brain with detail down to individual circuits.
We know which neurons fire when you see the color red, or when you feel pain. We can correlate brain activity with experience.
But correlation is not causation. That's the key. We can track the electrical signals in the blood flow, but the fundamental hard problem of consciousness remains.
How does the firing of physical, chemical, electrical neurons generate the subjective, internal feeling of being alive?
That's the critical gap. Why does seeing a sunset not just register as light processing in your visual cortex, but come with this unique, subjective, emotional glow of red and gold?
Why does hearing a perfectly mapped sound wave result in that deep, melancholy feeling of nostalgia when you hear a favorite song from your childhood?
The scientific tools we use to study the material world are excellent at measuring objective quantity, mass velocity, voltage.
But they can't access or measure subjective quality, the internal qualia, as they call it, the redness of red, the sorrow of sadness.
It's a leap from matter to mind that is, right now, scientifically inexplicable.
And there are theories that try to bypass the problem entirely. One camp suggests consciousness is just an incredibly complex form of computation.
A massive information processor. And once we build a machine that's complex enough, consciousness will simply emerge from it.
But others go much deeper. They suggest consciousness isn't an emergent property of the brain at all.
But maybe a fundamental property of the universe itself, like gravity or electromagnetism.
So in that model, the brain wouldn't generate consciousness.
It would act as a kind of antenna or a filter, focusing a cosmic field of awareness.
Which raises the even stranger question. If consciousness is fundamental, then what is the consciousness of a rock
Right.
or a galaxy?
It just pushes the mystery further out, but the central paradox remains. The most ordinary thing we experience, just being awake, is the greatest, most profound mystery of science. It slips through our fingers every time we try to pin down its physical origin.
And while we grapple with the nature of consciousness itself, let's look at the strange, powerful tricks the mind plays on us every single day.
Let's start with the placebo effect.
The placebo effect is stunning. The fact that believing a sugar pill will help you actually causes real, measurable biological change in your body.
It's proof that the mind-body connection isn't just some spiritual concept. It's a measurable pharmacological system.
Absolutely. The expectation of treatment can trigger the release of genuine endogenous opioids, the body's natural painkillers in the brain.
It can alter hormone levels,
Hmm.
affect your immune response, even change the brain chemistry associated with depression or Parkinson's symptoms.
It's basically a self-healing program that gets activated by belief.
But the really deep oddity, and our research really detailed this, is that placebos can work even when the patient knows they are taking an inert substance.
That's the part that breaks my brain. It's not just about conscious deception or hopeful thinking anymore.
No. It shifts the focus from simple belief to the power of ritual and expectation. The entire context, seeing the doctor, the white coat, the prescription, the act of taking a pill at a specific time.
That whole ritual taps into these deep-seated internal healing pathways.
The mind seems to activate the body's repair system simply based on the promise of treatment, regardless of what's actually in the pill.
It makes you wonder how much of modern illness could be tied up in narrative and expectation if the mind can wield that kind of power over the body.
And then you have the total opposite experience. Déjà vu.
Oh, that profound, unsettling feeling of familiarity. You step into a new room or hear a new piece of information and your brain is just screaming, I've been here before and I know exactly what happens next.
That moment where reality feels briefly doubled, it's so intense.
The scientific explanations mostly focus on glitches in memory processing, right?
They do. One theory is that it's a failure of retrieval. The brain sends a signal of familiarity. This is an old memory. But the retrieval system can't find the actual memory, leaving you with that hollow sense of recognition.
I've heard another one that it's a timing mismatch between the brain's hemispheres.
That's another interesting theory, and it feels very relatable. One hemisphere processes the sensory input a fraction of a second before the other, making the second processing feel like a repeat of the first immediate experience.
But the mystery is in the emotional conviction. It's not just a passing thought. It's a momentary, intense feeling that your reality is fundamentally breaking, that you're witnessing a loop.
These glitches just remind us that our perception of the past and the present is being actively constructed by this highly fragile, mysterious machine that's operating inside our skulls.
Okay, let's wrap up our journey through the deep unknowns with the most abstract, yet somehow most connecting mystery of all.
The uncanny effectiveness of mathematics.
This one is profoundly strange. Mathematics is a human construct. We invented the symbols, the logical rules, the theorems, the axioms.
And yet, these human mental tools describe the physical universe with an accuracy that borders on the prophetic.
Why should the universe care about our algebraic notation? It makes no intuitive sense. Why should a concept dreamed up by a Greek philosopher 2,000 years ago perfectly describe the curve of a planet's orbit or the bending of light around a galaxy?
The examples are just endless and staggering. Einstein didn't discover general relativity by looking through a telescope.
No, he derived it through purely abstract mathematics. He predicted black holes and gravitational waves decades before we had the technology to verify them.
Maxwell used math to describe electromagnetic fields, and that led to the prediction of radio waves. It's like the universe handed us the instruction manual before we even knew how to read the language.
Which forces the great debate. Is mathematics discovered?
Meaning it's built into the fundamental architecture of the cosmos, and we are just uncovering the blueprint like archaeologists.
Or is it invented? A tool we've painstakingly tuned and refined through evolution to accurately fit the patterns we happen to see. A powerful, but ultimately arbitrary language.
The power of math seems to lean heavily toward discovery, doesn't it?
It really does. The sheer fact that the same set of formulas, say, calculus, can describe the arc of a thrown baseball, the flow of a river, and the motion of distant galaxies. That suggests a deep underlying unity.
Why should abstract symbols map so perfectly onto physical reality across all scales? It suggests there's a fundamental layer of reality that is structured, logical, and accessible to the human mind.
And what's more, the laws of physics are built on a series of fundamental constants. The speed of light, the gravitational constant, the charge of an electron.
And we have no idea why these constants have the precise values they do. If they were even slightly different, the universe would be chaotic, or it wouldn't exist at all.
And mathematics can perfectly describe those constants and their relationships, but it cannot explain the source of their values.
It's the ultimate riddle. We have the ability to read the output of the universe's brilliant code, but we cannot access the source code that dictates the initial parameters.
The uncanny effectiveness of mathematics is, maybe, the ultimate hint that reality is much deeper than our three-dimensional time-bound perception allows.
We found a loophole, a perfect language to describe things we can't see, but the origin of that language is as mysterious as dark energy.
Wow. We have covered everything tonight. We started with the question of why anything exists at all, moved to the terrifying fate dictated by invisible dark energy, zoomed in on the impossible physics of black holes.
And we ended up contemplating the biological miracles of salamander limbs and the staggering predictive power of a simple equation.
It's a profound reminder of the limits of our knowledge. I mean, there are these massive silences we didn't even get to.
Like the absence of detectable extraterrestrial life, the unknown origin of Earth's vast water supply, the battle between matter and antimatter that somehow resulted in a universe made of matter.
And the beauty of this entire journey is realizing that mystery isn't a failure of science. It's the engine.
Every unanswered question, every single paradox is an open door. It's a profound invitation to keep exploring.
The human mind is capable of using mathematics to describe processes happening billions of light years away and predicting events millennia in the future. But the greatest mystery of all remains a cognitive one.
Is the human mind, which emerged from this strange reality, capable of ever fully comprehending the totality of that reality? Or is curiosity itself part of the mystery?
That is a truly provocative thought. To wonder is to be human, and to seek is to be alive. Thank you for joining us on this late-night deep dive into the unknown.
As you close your eyes tonight, let the weight of these cosmic secrets become a sense of quiet wonder. They don't need answers tonight. They only need to remind you that the world and the universe is far stranger, far more complex, and far more beautiful than we can fully grasp.
Good night. Rest well, and may your dreams be filled with wonder.
Yeah.
And maybe the occasional philosophical debate with a bowhead whale.